Let's go ahead and get started. So welcome. It's nice to see so many faces, so many new faces, people I haven't seen before. And this is CPRE 480/580. It's graphics processing and architecture. And I'm just very excited to be here today and to kind of be your guide and mentor through the next 15 weeks or thereabouts, where we learn about graphics processing together. I have that quote at the bottom, a little bit of flavor, but really it's intended to indicate that a lot of what is in this course is really kind of experimental in nature. And there's really no such thing as a failed experiment. I think you'll notice that and find that when you're taking more advanced classes like this one is. It's not as smooth and as streamlined of as an experience. There's rough edges around the kind of things that we do here, because we're trying to learn about cutting edge technology. We're trying to do cutting edge things in the lab experience as well. And you'll find pain points along the way. But that's not a bad thing. That's partially by design, partially just the nature of the complexity of the kind of things we're doing in a class like this. And I want you to have that mindset starting on day one. There's no failed experiment here. This is a class in which we kind of learn together. We kind of engineer fun solutions to interesting architecture problems related to graphics processing. And you put in a good faith effort, you'll be just fine in this class, despite some of the rough edges that you may find as you go. So everyone has kind of a different background coming into a class like this in terms of, the prerequisite is really just a computer architecture prerequisite, typically an undergraduate course. I'm also fine if you don't have computer architecture, but instead just have sort of like digital VLSI background and experience. But architecture, in terms of a CPRE 381 type of course, is what I typically assume a student has when they come into this course. But then the other kind of topic we were learning is about computer graphics. And definitely people have different backgrounds, either through having taken computer science or, of course, in other departments on computer graphics, or just your own personal experience and exposure to the topic. So I think we have to start off, although it may be a little slow for some of you who have studied this topic, just making sure we have the right kind of verbiage and terminology for what we're talking about. For a class that's called Graphics Processing and Architecture, what do we actually mean by that? So computer graphics, to start with, just at the highest level, deals with just all aspects of creating images using a computer. If it uses a computer and it creates an image, it is computer graphics. So where did this image come from? This is my other car, not the one I drove today. This image is an artist's rendition of a BMW M6. In terms of how it was modeled, my best guess is it was modeled using Maya. The renderer we are using, or was used to render this image, is called the physically based renderer. Kind of some advanced techniques for more realistic rendering of 3D objects that we'll learn a little bit about as the semester goes on. I just provided that link there if you want to take a look at some pretty advanced computer graphics, open source code there. And in terms of the hardware, underneath the application, which is the rendering, the software, which is how it was rendered, and then the hardware, some sort of PC with some sort of graphics card for doing that modeling and rendering there. So in terms of terminology with regards to this very broad field of computer graphics, we can categorize things first by the particular specialty inside computer graphics. So some of you have more of a double E background, may have learned about image processing, either through projects or through courses you would have taken. The term used in the computer graphics community for that is just imaging. So the idea behind that is you're representing 2D images. So anything about processing 2D images, we categorize that as imaging. I already used a couple of these terms already, but modeling is how we represent 3D objects. We do not do a lot of modeling in a computer engineering curriculum. That tends to be more of like a practitioner type of curriculum. How do I model that 3D car so it looks really good? Not the kind of thing you learn necessarily in an engineering curriculum, but it's still a very technical skill set that one has to build up as well. How do we represent 3D objects with reasonable fidelity? One of the key tasks we're going to be interested in is rendering, and that's taking our 3D model like of that car and building a 2D image from that 3D model. There's a little bit of math involved, but it's not anything beyond freshman level math, and a lot of architecture and software associated with that as well. And while this class, partially due to some just practical constraints of the type of hardware we are building, we don't do as much of it, it's certainly very critical to be able to do animation as well. So that's the rendering task of building 2D images from 3D models, and then allowing that rendering to kind of change and adjust and just move over time and simulating those changes. That's one way we can categorize computer graphics. That's at least the term modeling and rendering you'll be hearing a lot this semester. And then of course it can also separately be categorized, given those technical tasks, by the particular goal or task that we are using those specialties for. So we could just be creating pictures or movies on a computer. We could be using computer graphics to simulate some sort of physical phenomenon and visualize it. Separately, we can use computer graphics just to visualize information in and of itself. And then, not to even mention, like, just the video game industry, which is a combination of modeling, rendering, and animation, which is, a very large industry at this point, and pretty important in terms of the advancement of computer graphics as well as graphics processing. What does this kind of mean in practice? Well, we have all sorts of graphics for entertainment, right? We have the animation of what you could call non-interactive or sort of offline rendering for movies, for example. So this is just a frame from a relatively recent Pixar/Disney movie, and you can really see the attention and detail and the different lighting models here. We don't get into all of the details in a class like this of how the RenderMan architecture works and what algorithms are at play there. It is the kind of thing that I think by the end of the semester, while we don't really touch upon it, you'll be ready to dive into that after the semester is over. But it takes us more than 15 weeks to kind of get to that point. That's an example of offline or non-interactive rendering. And then we have examples, and there's so many examples of interactive rendering, maybe for entertainment purposes. That's Halo Infinite. Just a reasonably recent example of sort of real-time rendering and taking models, converting it to the best kind of highest fidelity 2D image, and doing that many times per second to get a reasonable speed of processing and rendering there. That's graphics and this quick little animation is just showing what the scene looks like before and after a particular lighting model is applied. There's nothing else you really need to take away from that example. That's graphics for entertainment, but for as many examples as there are for entertainment purposes, there's all sorts of usage of graphics for non-entertainment or for science and engineering purposes. Compared possibly to the scene on the previous two pictures on the prior slide, these may not look as impressive, but they actually are in terms of some of the complexity there. This is still one of the highest detailed mesh objects that is used to kind of stress test distributed renders. This is a model of a Boeing 777 with the engine as well. I forget the exact numbers, but it's in the hundreds of millions of triangles for the particular components there. And then just this example of a Helsinki city model where you could consider this maybe some sort of visualization. You could overlay it with other things as well. This is an example that has just a lot of mesh data, and it's many gigabytes of mesh data just for that particular scene of a city there. So we sometimes tend to think of graphics being pushed by more on the entertainment side, but it's really not exclusively so. So the needs of both of these examples are really pushing graphics architecture and the underlying hardware and software frameworks. That's very much the case, but these are doing so as well. They also have particular performance needs, particular scaling needs, and you see a lot of innovations and really separate types of innovations coming from both spaces there. In terms of this course, now let's bring it back to why you're here today. Our course, our primary focus here in CPRE 480, 580 is on graphics processing. So that's the software techniques and hardware architectures for accelerating rendering, and we'll say real-time rendering and related computational tasks. So that's actually covering arguably 4 different things in that sentence there. So software techniques, we have to learn those, and we'll see why I think it's sufficiently motivated. And hardware architectures for accelerating rendering, and then computational tasks. So there's a lot of related interlocking things going on there, but we're really going to be covering those 4 components there, both software and hardware, and then rendering, taking 3D model, converting it to a 2D image, and then the computational side as well. Well, why study this particular topic? Why study graphics processing? I guess I don't need to convince you, you're already here, but in terms of why this is a course in our curriculum, why it's an elective that we like our students at both undergraduate and graduate level to take, I think it's just a very interesting problem with a completely separate class of algorithms from what you would learn in your other courses if you weren't studying computer graphics. And without a doubt, it's definitely challenging implications for both processor and system design. If you've taken other computer architecture courses, depending on what you've taken, you've certainly learned a lot about, we'll call it general purpose computer architecture. Depending on what you specialized in, on the embedded side, you've learned more about embedded architecture as well. There's a course that covers machine learning architectures, and there's a little bit of overlap between that course and this one. And then separate from all that, this is computer architecture for graphics processing, and we're really going to focus on what's different about this class of problems and the resulting processor and systems design for it as well. And then just generally the relevance of the problem given the programmability of modern graphics processors and the applicability of the same architectures we're learning about for accelerating rendering, their applicability for high-performance computing. It's becoming just an increasingly important system design challenge, architectural design challenge, really pushing the envelope of computing systems in general, and certainly in computer architecture. And it's a moving target in a good sense, I guess. If you take CPRE 381, those of you who took that course, it's a pretty stable type of material because even as new general purpose architectures are coming out, they have so much in common with prior generations. And really that course doesn't look any different from what it would have looked like in 1995. Although it's still modern and relevant, it has not evolved at nearly the same pace. Graphics architectures are evolving at still very much a breakneck speed. So we learn a given snapshot of rendering and computational hardware in this course. And then if there's something you want to study beyond that, you're ready to go. You're ready to learn about that additional material. Certainly those of you who are in the 500 level version of this course who are presumably graduate students or planning on becoming a graduate student, that's where I'm hoping a course like this can take you. You learn some fundamentals in this course. You're then looking for master's or other kind of graduate level projects. You can kind of take what you've learned here as the basis for creating and coming up with ideas for that project. So one question I sometimes get with why we have a course that's so hardware focused, and this is very much a hardware course. There's different versions of this same question. I'm a computer engineer. So how many of you would call yourselves computer engineers in this class? Show of hands. How many would call yourself electrical engineers? Software engineers? Good. Okay, fine. I understand that. Software person. So for a large percentage of you, computer engineers. So I'm a computer engineer. I do hardware, not algorithms. Can we just skip ahead to the architecture? Flip side question is also valid. I'm a software engineer. I do algorithms, not hardware. Can we just do the algorithms? It's kind of the same question from just two different perspectives. And my philosophy, and I think it's not just unique to this course, is the answer is not really. I don't think you can easily understand 3D graphics architectures without understanding the 3D graphics algorithms. And while some courses do attempt to teach algorithms without the underlying hardware, I don't think you can truly understand the evolution of those algorithms without also understanding the underlying graphics architectures, because they very much co-evolve. The architecture strongly influences what applications are possible, and the applications and the algorithms strongly influences what the next generation of architecture looks like. So it is this kind of constant feedback loop with the end goal of, how can I get the best possible 60 or 120 or whatever 240 hertz image for roughly $100, $200 worth of silicon real estate. So that whole evolution is a constant, and you can learn just basic graphics algorithms, but understanding how they came about and what the next generation is going to look like is not possible in my philosophy, in my opinion, without also understanding the graphics architecture. Likewise, you can learn graphics architecture in a silo, in kind of isolation, but really understanding why it is the way it is really not possible without understanding the evolution of algorithms and applications as well. So in this class, we study both. It is very much an architecture course. So those of you who want to do more digital design and want to understand more architecture, you're in the right course, you're in the right place. We do have to study the applications, we do have to study the algorithms. We need to be able to write software that makes sense for the underlying architectures that we are working on. That may not be super duper clear right now, but I think it'll become clear as the class kind of progresses. Here is some of the syllabus related things. Quick show of hands, have you accessed Canvas yet for the course? That's not bad. That's not a bad number. Okay, we'll take it. It should be ready to go and complete with all the materials. I like to have Canvas kind of set before the start of the semester, and then I don't have to touch it too much. I organize it by learning modules. That's not meant to be a lecture. Sometimes it's a lecture. If I find myself just talking too much, I'll try to break things up and do something different in class. Roughly 10 learning modules, 10 different modules that we're covering here. In each of those, there'll be in-class exercises, there'll be a couple technology demos. The other major component of the course are the 5 machine problems. That is a term that's kind of fallen out of favor. You can call them labs if you want. There are 5 major lab experiences for this course. That term used to refer to that you're building a machine for each of these labs. They are labs that have significant hardware and software components to them, because as we're learning graphics architecture, we're understanding both software and hardware and how they co-evolve. Each of those machine problems are going to have significant components there. And then there's going to be one final project, which is really just meant to be kind of an extension of those machine problems for the last few weeks of the semester here. That may sound scary. I don't know. Depending on what courses you've taken, if you've had courses that have had a similar organization to this before. But as we talked about kind of the grading components here, these are meant to be the significant kind of lab work / homework associated with this course. They are not simple. They will take you time. It's going to be team-based assignments. You essentially have no individual work in this course. It's entirely based on your team. And then taken in totality, that is the grade for this course, is the work you do on those machine problems. So they are hard, they will take you time, but that is the entire course as well. So I think it's okay. There's not going to be quizzes, there's not going to be exams, there's not going to be separate little homework assignments where you're turning things in on a weekly basis. You have these 5 things to work on this semester plus the project. They are not simple, but that is what you're working on for this course. That is what you are learning by doing in this course, are those particular machine problems. Let's meet the staff. That's me. My office is just right upstairs. I'm going to try to hold my office hours from 11 to 12 on the days we have class. Really, when you need me, just let me know, though. It's hard to say what times would work for any given class, so just ping me, and we will make it work. Jeremy is here today. Everyone say hi to Jeremy. He's hiding in the back. He is our teaching assistant. He is a CPRE 480 alumnus who knows his stuff. I told him his job is not to scare you at all in lab, but he's gone through the class, he's made it out the other end, and he's stronger for it. And he also has office hours, and of course I'll be here during the lab time as well. I'd also add that, given the relatively modest size of the class, we only have 5 hours of Jeremy this semester. So I've also brought in additional teaching assignments. That's Joey, age 14, also sitting in the back of the class. Tessa and Johnny, who are not here, they help me with grading as need be here. They'll work tireless for you. So Jeremy, we only have for 5 hours. I can get 20, 30 hours. I don't have to pay them either out of the kids. So between them and of course myself helping out as best I can, I think we have enough to make it work. I'll also mention this. I don't recall if I have a slide about this. My goal for a course like this, anything 400, 500 level, I kind of want it to be just like a community of people learning together. That doesn't mean we have one large, 15-person team on the assignments, but I want you to be helping each other out as well. It's not a competition in any real sense. I want every student in the class to get an A in the class, and I want you to learn a lot, in the process of getting that A in the class. But we've got Jeremy for 5 hours. We've got, me as available as you need me. It's very much expected, and I'm hoping for helping each other out. There'll be a couple late nights this semester in the lab, possibly, and if you're there for each other, helping each other out, that would be wonderful. That's not a bad thing in this course. I actively encourage you to help each other out. So communication is always key. I think in a course like this, some of the things you are designing are going to be hard to both design, implement, and debug. So you need to be able to communicate with the instructional team when things are not going well, and let us help you. So Canvas is primarily as the class web page. So I'll post announcements there. All the documentation, usually you can Google and find it anyway, but it's all on there as well. That's where you'll be doing sort of online submission and getting the grades for the MP assignments there as well. But it's a pretty static thing. If you access it once a week, that's probably sufficient. I'm also going to try to use Discord again this semester for our class discussions. If we have to have any virtual kind of office hours, we can use Discord for that as well. For team-based work and discussion, that's where I want to use that. That link is directly on Canvas as well. You don't have to write it down or anything if you haven't joined yet. I'd like you to use it. It's a third-party software. I can't require you to use it, and so I'm not requiring it. But if you have a question of me, either technical or non-technical, you'll get a much faster response from that than sending me an email and being one of 400 emails in my inbox when you send that to me. So that's my recommendation. If you have questions, of course, with Jeremy, of the class in general, for clarification on an assignment you're working on, just some technical questions you may have. I kind of want us to use it. That's my goal. That's kind of our active kind of online thing. This course, when it was most recently recreated back in 2000, was an online course. We only had the Discord available to us, and it worked pretty well that semester. Last spring was kind of a bit of a hybrid of mostly in-person plus usage of that. We'll see what works best for this particular group of students. But if you're already on it for other courses or for other projects and things like that, I'd like you to also add that server and try to be active there. Any questions before we keep going with this? Sure.
So I saw on the Canvas page that the modules tab isn't open. Is that where all the lectures and slides would be?
Yeah, and I think I have the web page open here, or the Canvas page open here, kind of in student view. I'm stubborn. So when I'm told, I always used to have class web pages, and when told I have to use Canvas, I basically made a class web page on Canvas. But I think it works well. You let me know how well it works on your phone and things like that. So the main navigation point would be the schedule page, which is kind of got like day-to-day schedule stuff there. All the lectures, all the assignments. You may not be able to see that first assignment yet. We're going to talk about that because that's assigned to groups and we don't have the groups yet. But for example, you click under week 1 introduction. I think I got the right dates there. And it's in decent shape. I don't know if it's perfect. Just let me know if there's any bugs. Lecture slides, if you want these slides, they're available. I have videos from when I last tried to record this. I will update those with the most up-to-date videos. And that's what we'll have for every one of those assignments. And that's where you will go for the first lab assignment, which is going to be starting this Wednesday, tomorrow in lab. A little bit of this is like the student view where it sees where you're trying to attempt it. Some documentation on just lab policies. Jeremy's going to walk you through all this tomorrow in lab. One nice feature of Canvas that a web page doesn't give me is it provides a way for me to kind of give you kind of a grading rubric, which is sort of like just a mini contract, right? It's like, okay, you're working on this assignment, do these things and you get this grade, and it's meant to be that you get a 100% on every single one of these assignments. That doesn't mean it's simple. That doesn't mean it's not going to take some effort. So I'm not saying that. I'm saying it should be very clear what grade you're going to be getting on these assignments based on what you're doing for these particular assignments. So that would be how I would try to navigate through Canvas. Treat it like a web page. Syllabus information is all there. The resources page I briefly mentioned has like the PDF guides for some of both the software frameworks and the hardware frameworks that we are using in this course. It's hard to say. It might just be easier to Google it at the time you need it versus trying to look through this list and find it. But everything I put on there is because I thought it would be useful for one particular component of an assignment in this course. It's not just a random collection of links. But that's what I have there. And then we have the Discord as well, where I think is where you'll be hopefully asking questions as we have them there. Thanks for asking that. I never really looked too much at how it looks like from the student view. Yeah, sure.
Is that first MP0 assignment, are we going to have our groups by tomorrow then?
That's my hope.
Okay.
We'll see how it goes. Yeah, that's my hope. So that's the plan also before we leave here today. That's why I'm checking my watch here. Also listed, I think I provided the PDFs there, 3 recommended but not required books. There's no required textbook for this course. These are 3 that I have used that I think are helpful. They're also good bookshelf references too, so there's no harm in having access to them, I would certainly say. The first one is Ed Angel's book on interactive computer graphics. It's getting a little bit dated at this point, but in terms of understanding 3D rendering using a very traditional OpenGL-based shader approach, it's pretty decent. It's definitely meant to be a textbook, so I think it's a useful resource to have for that purpose. Got really nice visualizations in there as well, so it's a pretty cool book to have. I have a copy, but I still sometimes reference it as well. Second one is the real-time rendering book. That is a pretty advanced tome. It's really good to have on your bookshelf. I think you'll appreciate a lot more of that book by the time we get to week 15 of this class, but I think it's a very good one. It does not cover, it has essentially zero overlap between the content covered here and the content covered here. The Ed Angel book is pretty much, again, traditional rasterization-based rendering approaches using OpenGL. This is what do you learn once you're done with all that, essentially. And we will be touching upon that and exploring some of that, but it's a bit advanced, for that reason. And the third is kind of the red book, the guide to doing OpenGL-based programming. We will be doing OpenGL in this course. Really, we'll be doing just enough OpenGL to be able to interface with the hardware that we are designing. Kind of like in 381, you do just enough assembly to be able to interface with the hardware that you are designing. You're not becoming an assembly expert by any means, but that resource is pretty good to have because OpenGL can be kind of miserable at times. And the truth is, this is a very large book, and everything we want to support in OpenGL, we have to do it ourselves, as you learn about the lab infrastructure here. So we take a very small portion, hopefully strategically selected portion of that book, and those are the API calls, those are the functions you have to be able to understand. You do have to be able to understand those pretty well, so that resource is useful for that. If we wanted to build a truly OpenGL compliant GPU, we'd have to implement the entire book. That would take us a little bit of extra time. So there's our view of the week on a day-to-day basis. Today is Tuesday, so you have us here together in class, plus office hours. Please feel free to stop by today. With labs that are on Wednesday, and for the most part, we'll be having them due on Monday nights, not due on Tuesday nights. So we will talk about that kind of weekly cadence we have in the class. But you have that big block of time on Wednesday to get started on the labs. All the labs are at least 2-week experiences, so you certainly don't have to feel you are done with it. My goal is always, by the end of that first week of a lab for one of these MP assignments, is that you have a plan, like a real plan. Not, hey, we'll get to this later. But, okay, we understand the problem. We understand what the challenges are. We're splitting up the work, or we're going to meet again tonight, or whenever it's going to be to get it done. That's really the goal. After the first lab for an MP assignment. For the second lab, it should really be kind of getting together, synthesizing designs, literally and figuratively, but like combining designs and also then debugging. And then we have kind of our final get-together in class where we're going to have these kind of demo days for these assignments. So there's these 5 major machine problem assignments. They're roughly 2 weeks each, then with the remainder of the semester being spent on the final project. That's going to be the kind of regular cadence of the class as we go from a week-to-week basis. The reason Jeremy's office hours are on Monday night is because I'm wanting you to submit your assignments by that Monday night so that in class on Tuesday, we can go over them together and kind of talk about what went well, what didn't go well. These aren't always celebrations of success. Sometimes they're kind of commiserating of failure as well. It's a combination of both. It should be a fun atmosphere on Mondays in the lab. Okay, so I've already talked about it a little bit, but let's kind of make sure it's relatively clear what we're talking about with regards to these so-called MP assignments or machine problems assignment. The semester-long goal, what you will have accomplished by about 10 weeks into the semester, and then whatever you add onto it for your final project, is the design and implementation of what I've referred to as my simple graphics processor, or SGP. So you are building a GPU, a graphics processor in this course. And not only just sort of a toy GPU, it's also going to be a roughly OpenGL compliant GPU. I said that really large red book we have there. We're pulling out subsections of that, and that's what we're supporting. OpenGL is massive. But roughly, with a little asterisk or two, OpenGL compliant GPU that we are building in this course. We're going to start with relatively simple fragment processing, which is a term we'll talk about, but pixel processing we're going to start off with, and then we're going to continually add features. The idea there is that you always have something throughout the semester that is working, and then you're showing that by adding more architectural features, by supporting more things in OpenGL, and at the driver side that you're implementing, you're able to show more functionality and what's happening in the hardware. End of the semester, my goal is always a real game running at the resolution we've specified at. I have since discovered that is a slightly optimistic goal. Frames per second is a very common performance metric of graphics hardware or of software running on graphics hardware. 1.5 frames per second is not very good, right? That would be very painful if you were trying to play a game. That means you get 1.5 frames changing every second. It would feel like the screen is basically frozen. For the GPUs we are implementing, now, in our defense, in your defense, in my defense, we are trying to run it on an FPGA board that is very cost affordable, that is very modest in terms of resources. We also have modest amount of developer resources going into both developing the class as well as working on the labs. But for ours, ultimately, we have most of the API calls to get Quake working, but I think it'd be measured closer to frames per minute than frames per second in our implementation of it. We have gotten it working in the past, but we wanted to make sure we added sort of programmable GPU logic, and we'll talk about what that means. And that part we erred on the side of slow but doable versus really high performance programmable shader logic, and that's where the performance really started to kind of tamp down here. So this is a hardware course. It is okay, as you see some of these terms here, that you are new to them. So if, just out of curiosity, and it's fine if you haven't even heard of it, how many of you have used Vivado before? About half, and that's fine. I may want to have groups that are half have used it, half have not used it, versus entirely have not used it. That is the FPGA design software that we are using to design the underlying logic for the architecture. Also then for simulating and actually implementing on the underlying FPGA board. Vivado is arguably awful, but it is also kind of like state-of-the-art and the best tool available for us for doing FPGA design. I happen to have it open here. I was playing around with stuff before class. This is kind of what the end result of your design will look like, not the starting point of where it will look like by the end of the semester. A lot of this stuff I provide for you, and we will get a chance to walk through all of this as needed. The main component, I call it graphics subsystem. You could call this is the GPU part of your design, is within that block. And there's a lot of FIFOs there, which make it look more complicated than it really is. But there's really we're missing one here. 1, 2, 3, 4, 5, 6 components that you're working on this semester. 2 of them really go hand in hand, as we'll see, roughly corresponding to the 5 machine problems you have, and then roughly corresponding to learning modules where we learn about the algorithms and the underlying hardware for it. So it looks bad, and it is kind of bad. There's a lot going on here, but we scaffold our way up there. We don't start with a blank slate and say, hey, design a GPU. We start with kind of a working system that is a functional embedded system with you can get data in and out of it, and you can display the result on the screen and corresponding to that region of memory. And from there, we look at, okay, we want to add a rasterizer is a pretty good example of where we spent a lot of time this semester. Given a triangle, can I fill in triangle with the right color? In class, we'll talk a lot about the algorithms for how to do that. I think that's just a very fundamental algorithm in computer graphics. Then in lab, we'll design the underlying architecture for it, and then you'll be working on Vivado. And ultimately, it's not that many lines of code. It's not a matter of quantity of code you're working on for a course like this. What it is, and I'll just be upfront with you now, I don't want you to be afraid of it, is a lot of, I would call, very advanced debugging techniques that you'll be learning or just kind of developing or just stretching those muscles if you already have those in place. Because in most other classes, again, it depends on your background, when something isn't working, you at least know what part of the tool chain to look. Okay, it's a software bug. open up my ID and check my C code or Python or what's going on here. It's a digital design course. Okay, so one of my gates is wrong. I've done something wrong there. It's never the driver in any of your other courses. Well, but in this class, it will be potentially, right? Or it could be some really subtle interaction between logic you designed, driver code you updated, and then how you wrote your OpenGL application. And you have to be able to do that kind of full stack kind of debugging and tracing down of those bugs. You're not going to be writing lots and lots of code, but for even the code to just render a single red triangle on the screen, there's a lot of debugging skills that either if you already have, that's great, or you'll be developing through this course. That's why the assignments are not trivial. They are not straightforward, but I think it's a worthwhile experience as well. I mentioned this here. We have our own custom OpenGL library we've created for this purpose. The idea is that you're going to be able to write your OpenGL application, be able to see it running on the actual machine itself, the machine in Cougar 2050, to see like the red triangle or to see Quake or whatever you want to run in OpenGL. And then we have our own driver that we're running on that's going to be able to display the results natively on the workstation. And then it's also going to be able to kind of effectively encode and transmit those driver calls to the FPGA that is connected to that workstation there. Most of that is already there for you. For each assignment, you'll be kind of adding to it and saying, okay, the driver does this much. We need to have to do a little bit more. Let's add that. Let's debug that component there. So each of these MPs, again, my goal is not to scare you. If I scared you a small amount, that's okay. It wasn't meant to entirely frighten you. Each is going to have a significant amount of architectural design, HDL, your Vivado development, software development, although it's not a very heavy software course, and then really the heavy part is that integration and testing. But it can be done, and many students, the only example I have here in class today is Jeremy, have made it through the process and have come out for stronger on the other side. We have not covered any algorithms yet, of course. It's the first day of the class, and we have our first MP starting tomorrow. So MP0 is more of a platform introduction kind of lab. It is still a relevant design experience. It is not code. I guess I think the fair way to say it, it's not code that's going to go directly into this Vivado design that I was just showing you here previously. This is where you're going to get started tomorrow with your team once we have teams in place. So you're going to be designing and implementing a processor to perform matrix vector multiplication for matrix and vector sizes of 4. This is actually a very common, extremely common computation in computer graphics. So it is a relevant design, but the actual software application here is a very synthetic one. We're not rendering anything here. We're just doing a lot of matrix vector multiplication. Those of you who've taken the machine learning architectures course, you probably did something not so terribly dissimilar from this in terms of understanding the algorithms there. But here we're taking matrix and many vectors, and we're doing matrix vector multiplication of them. The idea is less so that we need this IP core for further components of the graphics processor we're building. It's really all about team introduction, platform introduction, getting used to the tools and techniques being used in this class. It is I think kind of a fun assignment because it adds a sort of one-off assignment where we don't need to use the code you've designed in any further labs. You're really free to do really whatever you want with it. There's very few restrictions. My suggestion will be, and we have a couple weeks to get through this point, will be, start with a very boring design. It's okay to be boring. It's okay to have very vanilla design. Start with that, get that working, get your 100%, and then worry about, okay, let's do something really creative with it. It's the kind of design, as you will look at the MP0 problem assignment, that there is a lot of opportunities for optimization. I fully support you trying all those and maybe kind of competing a small amount about what kind of design can get the best runtime for it, but start with something basic. Start with something that you know works, get your full score, and then if you have time, budget, energy, desire, have that be an opportunity to kind of show what other things are possible there. We provide, like in all these assignments, a lot of the overarching FPGA infrastructure, but then the actual implementation is ultimately going to be up to you. And you will see that as we talk about this as a class that is, algorithms, applications, sort of middleware, if you want to call it that, underlying architecture, and then digital design. There's kind of those 5 components of the hardware-software stack here. This assignment, although it is a very synthetic application and algorithm, really does potentially cover all 5 of those. And the opportunity for optimization could be anywhere within or all cross-cutting layers of that particular stack. The more optimizations you make, the harder it is to debug what's ultimately happening at the end of the day. But as you have a team, and I think given the class size, we'll limit to size 2 and size 3 teams. I think there's 14 of you in class. That's my head count I have right now. So mostly teams of 3 and then maybe one team of 2. Maybe each of you can take different aspects of the design you'd like to look at for doing that. But in order to do so, that's the first kind of in-class exercise I would like us to do. We actually have plenty of time, so that's wonderful. Let's do this now. So actually, if you can open up Canvas, if you haven't yet, and you won't always need to do this, but I'd like us to do it now in class because my life gets a lot easier if everybody does this now and I don't have to wait for anybody. If you go to the schedule page, it's going to be the one listed under Other, and that is Team Formation Survey. It says it's due tonight at midnight, but I want it done right now. So let's take just about 10 minutes and do this right now. And the kind of questions it's asking are to allow me to better kind of form teams here. I want to know things like what times are you generally available to work on a class like this, as well as kind of what other workload you have this semester, as well as like your comfort level in some of the major focus areas of technical design needed for the lab experience. I don't think this will take us more than about 5 minutes, but let's do that now. Then I'll have all that data. Tonight at some point I'll collate that and assign you to your teams for lab tomorrow. And if there is any one takeaway from today, it is that we do have lab tomorrow. I'll post an announcement about it, but come to Coover 2050 tomorrow, introduce yourself to Jeremy and your team, and get started. But let's work on this right now. for submitting that. Tonight I will form teams, and you'll just be able to see your team in Canvas. I can also, if you're in Discord, I can kind of label you as being on a certain team in the Discord. If necessary, we can revisit this mapping of students to teams, maybe at the halfway point, or week 5 or week 10 of the semester. If we need to reorganize teams, we can. It should not be a constant reshuffling. You will find that as you make progress on these machine problems, not for MP0, but afterwards MP1 and MP2, it'll be kind of hard to switch from team to team because the designs will start to look a little bit different from each other. And it's not impossible, but there's some design overhead, there's some effort required to design a module, and there's a separate amount of effort to understand someone else's module, right? So it's not necessarily a free thing to jump from team to team, but we can revisit and reorganize as needed. As you submit the MPs, there'll be a write-up. It's not meant to be super lengthy. I try to make your life and my life easier by saying, in your write-up, please answer this question, please answer this question, please answer this question. One additional thing for every MP assignment is I do want to know the rough effort percentage if it's a 3-person team for a given submission. It never needs to be perfectly equal. I mean, life's not equal, it's fine. I just want to know if, it's not 1/3, 1/3, 1/3, that's fine. I need to know if there's a 0% effort for someone in any given week. Again, people's schedules get busy at different times. Some assignments you really are better at than others, and that's always fair. It doesn't need to be perfectly equal. It is a team grade you get for these assignments, but I kind of just need to know when it's not working out for somebody, so we can reorganize or figure out what to do next as needed. And the reason I asked that first question about your availability to work on the labs, and I think it's fair game in this course, is for a 2-week lab, you will have 2 lab sessions, or 2-week machine problem, 2 lab sessions to work on it. They're 3-hour labs, so 3 hours this Wednesday, 3 hours next Wednesday, 6 hours, because there's nothing else in terms of what is due in this class. There's no quizzes, there's no other homeworks, there's no midterms and things of that nature, no reflection assignments. The expectation is you will not be able to complete the machine problems within that 6-hour time range. It may take you 7 hours. It may take you more. I don't know. It depends on the assignment, depends on the team. It may take more than it is designed to take more than that 6-hour time. Your time in lab is basically a guaranteed time that the entire team is known to be there, guaranteed time that like Jeremy is there to answer questions, and a guaranteed time like the whole rest of your class is there as well as you're working on things. 1 week should be really planning, ending it, everyone knows what they're doing and has a good plan for what they're going to work on. That is your homework for the week, right? That is your other assignment for the course. Second week should really be about integration and testing, coming up with a list of major things that need to be fixed for the upcoming deadline for the assignment. So that is the expected kind of, as I said, cadence of this class. You have the lab. It's not like a 200 level, 100 level lab in one of those courses. It's to get you started. It's to give you some guidance as needed from Jeremy here. But otherwise, it is the major work you're doing in this class is those labs. You're not going to get it done just in that 6-hour block. Yeah.
Are there many other courses using the same lab space as us?
CPR 381 uses the lab space. They should only have a few labs this semester. It's much smaller in the spring than it is in the fall. I do want to talk about that, and I was going to demo this as well, except I couldn't get it working this morning, which is not a good sign for you guys. But I will get it working eventually, and you'll be able to get it working. So we have the 2050 Cougar labs, and generally there should always be enough spots in there for your teams to work. I also have the remotely accessible lab infrastructure that was created when we first had to offer this course entirely online during COVID, the year that we had here. That is still in place. It's not as ideal, I think, as working in front of a nice machine, dual monitor setup, but it does work, and that is perfectly valid approach for teams. You'll have your own dedicated server for your team to work on labs. When what happens with these tools, it's extremely common. It's what would be a late hour for students of your age? Let's say it's 10:30. It's really late at night as you're working on an assignment. That was meant to be a joke. Okay, it's 2 a.m. You're working on an assignment. It's very common you want to try one more idea. As we get later in the semester, trying one more idea may take a few hours, for better or for worse, because the tools tend to have to deal with a lot of complexity. There's a lot of hardware that has to get designed. What'll be really nice with the remote infrastructure will be then, not as your primary go-to for getting work done, but you want to try one more thing. You kick it off on the remote infrastructure, come back to it the next morning and see what kind of results you get back out. I wouldn't recommend it as like, just from my experience, it's a little bit slower, it's remote versus being kind of local. And as we're doing graphics processing, there's a couple compromises we had to make, so it's even more remote than typical remote environments, as you'll see here. I'll try to demo that on Thursday with the remote infrastructure if I can actually get it fully working. It's nice to have, certainly when you don't want to be in the lab at a particular hour and you still want to get a little work done. That's a decent way to do it. The other nice thing about our infrastructure is even starting in MP0, Vivado is the primary tool we are using. I'll be specific, I don't trust anything other than Vivado 2020.1.1, which is the version I have installed here. Everything should work in more recent versions, but I just haven't tested it, and I'm not going to support it if it doesn't work. You can definitely install that locally on your machine. And then the way our lab infrastructure is set up, for this particular design, I want to program an FPGA with this design. And you may say, well, how are you going to do that? There's no FPGA connected to it, but we can remotely program the FPGAs as well. So that's a pretty nice feature, depending on the capacity of the capabilities of your laptop versus one of the workstations. This is a pretty nice way to get work done as well. This you just take with you. You tell it to hit and run and synthesize a job. You let it go overnight sometimes, or at least 45 minutes. And then when you want to program an FPGA and test the results, that's where the remote infrastructure can be very useful. I'm connected to a machine that's currently in 310 Durham right now, xilinx-6.ece.istate.edu, and it says it's programmed, but I'm going to click and program the design again. And that remotely program that FPGA. So we built all that infrastructure by necessity, because we didn't have a choice really to do FPGA work remotely, but it's still there, it's still very useful for that purpose. Definitely you have to kind of shepherd your time carefully when doing advanced digital design or FPGA work. You may get this feeling of like you're productive because you're staring at Vivado for 3 hours, but it's actually just compiling, the whole time. And I want you to avoid that. Like, I don't want the labs to become that kind of experience where you feel like it's consumed your whole life. They're not supposed to be. Work as a team. Come up with the next fix you're going to work on that you're going to debug. That's not trivial, but come up with that, implement that, and then get out of there and come back to it in a couple hours or however long it takes to do that run, or work on something else, work on the write-up for this course, or work on something else, so that you're making a productive use of your time. And likewise, as you get into the real weeds of designing this stuff, graphics architecture, don't just go willy-nilly into it. Let's try the value of 7 for this number. Oh, 7 didn't work, let's try 8. Let's try. For software prototyping, doing some quick little C programming or C++ or Java, that's fine. When doing hardware design, we can't have that philosophy. We have to be a lot more, I would say, careful and intentional about what we do, because the design cycles are so much more time intensive and painful. But I have tried, based on my understanding of having to do it myself as well, try to eliminate a couple of those pain points, and this is one example of being able to access basically the same exact designs and boards in Cougar 2050, just remotely accessible versions of the same. This was meant to be my demo of the remote FPGA infrastructure. I just showed off like a fourth of it, so that's going to be good enough for now. So we have Cougar 2050. That's the lab. That's the architecture lab on the second floor here. That's all you need to use. It's not a requirement you use any remote FPGA infrastructure, but we do have this. And with Jeremy's help, we'll do a little bit more debugging and confirm that it all still is working. And we have that so we can remotely deploy stuff that you don't need to be physically in 2050 to do some testing here. What makes it a little bit more challenging for this nature of class versus any other type of class is it is a graphics class. And we want to render and confirm that the triangle is red that you wanted to put on that screen at that part, and it's in the particular location you wanted it to be. That's an extra little bit of challenge, both from like a Linux perspective, there's extra challenge associated with that, and also from a physical instrumentation perspective. So we do have the ability to remotely monitor not just the FPGA boards, and that's what Vivado provides for us, but we can remotely monitor the actual cameras we have connected to those particular FPGA boards. Every time I say that, I go to try it, and it's not necessarily working. Let's try one more thing. I said this was an experimental class. There you go. So that's the remotely accessible monitor in 310 Durham, connected to whichever team is going to be Team 6. That'll be your monitor if you need it. And let me just say it one more time: you are not required to use any of the remote infrastructure. When it's 2 a.m. and you still want to try one more thing, it's probably going to be more fun to do that than to come back to Coover and try it there. That is all the downsides, all the upsides of having remotely accessible, but all the downsides as well. That is a camera pointed at a screen. You are going to eventually want it to be testing at almost like a pixel level. Is this pixel red or is it purple? And that can be very hard to do within this infrastructure. Every so often, there's like a smudge on either the camera or on the monitor, and you'll convince yourself your design is rendering something incorrectly, but it's actually just a smudge. Sometimes one of the grad students bumps into it and moves it off by 6 inches, and then you have to wait maybe until the next day to get that fixed. But this is there available. This is a live stream of that room monitored by grad students, and it's there for you to be able to remotely deploy stuff, remotely test stuff. And we have some Discord-based automation for some of the same as well that you may find useful, although none of it is strictly necessary here. I mean, that's some of the infrastructure. What I wasn't able to get working with, I was having a driver issue with OpenGL, so we will not show that today, but that's the crux of what we have there. We also have cameras that are pointing at the FPGA boards themselves. For most of the stuff we do in this class, it's not as necessary. There's very few things that require that this light be, this LED be turned on or not. But that can sometimes be useful from a debugging purpose. Sometimes as a sanity check, it's very critical to know, is the design that I'm testing very carefully, is it actually the one I think it is? Or was this yesterday's design? Or is this my teammate's design and not my design? And anything you can do to improve upon that kind of convincing that you're actually running the code you think you are will potentially save you some time here. Just a couple more things, and then I think we'll just wrap things up here. Here is the high-level learning module outline. I'm hesitant to say the course starts off a little slow the first couple of weeks. There's just some background technology I feel like I need to make sure everyone's on the same page for. So I call the next learning module after we finish up introduction on Thursday of, here's all the stuff that you may know or may not know just to make sure we're all on the same page. That's what I call enabling technologies. That'll just take us a couple days of class. It's probably 60% review, but the 60% might be different for different people. So it gets us all kind of on the same basis there. Then we learn just enough OpenGL to be able to start using it. That's learning module 3. As we start to learn about the different aspects of the graphics rendering pipeline. And at that point, the learning modules start to directly correlate to what you'll be doing in lab as well. So this first lab is all about just learning about the platform, getting familiar with your team and with the tools that you'll be using. Then as we start to learn different aspects of the graphics rendering pipeline, we'll be learning about applications and algorithms and architecture in class. You'll be implementing it in the lab. And there'll be a pretty direct connection between the two for those periods of weeks. Going up through textures and lighting, we do textures for the very last MP, but we do not do any lighting. Other than just what lighting you can do via programmable shading. And then, it kind of disconnects from the lab at that point. Frankly, it's a lot quicker to talk about viewing and transformations than it is to implement it. And so we try to stay synchronized, but it's a little bit of a challenge. Then we start talking about what you can do with the GPU hardware beyond just, real-time rendering. How you can use either the same hardware or evolutions from that same hardware to do really high-performance computing with it. Then it, of course, kind of transforms into, at least in class, a kind of a CUDA course, learning about that framework, those tools. Again, some of you may know how to do that already, but otherwise, we can spend as much time as needed learning about how to do high-performance computing using CUDA. I think the nice thing and the advantage you would have over someone who just took a Introduction to GPU Programming course is you'll have a much deeper understanding of the underlying architecture versus someone taking just a CUDA course knows the magic words to get decent multi-threaded performance out of design. You would actually know what's actually happening, why what we're doing when we do GPU computing has a direct connection to what you've learned with the things you've designed in lab and the algorithms, applications, and architectures for real-time rendering as well. Finally, the last thing I want to mention here is just the final kind of syllabus items here. These are the grade components. I think it's fair. You'll be spending the majority of your time out of this room on the machine problems for this course. And the final project is just an extension of that. So you would say that 90% of your grade is based on your lab in this class. With 10% of class participation, that's kind of vaguely defined here, although that's kind of some of the things I mentioned there. Just come to class. There's only 14 of us, so if like a lot of you decide not to come to class, it's going to get kind of weird pretty quickly. So please just come to class and just try to be active in the class. So helping others, making suggestions, being active in class discussions, challenging me to be better. This class, as I said at the very beginning, is balanced on the cutting edge of some relatively new but relatively fragile technology. It's not intended by design to be completely smooth. In practice, it's not completely smooth. This is a class you'll have to put a decent amount of effort into. I don't want you to be afraid about it, but I don't want you to be stressed about it either. Because if you do your job in this class, you will get an A. Every student who took it last spring got an A. I don't know if I'm supposed to say that or not, but everyone did their part too. So it's not as if I just gave everyone A's. Everyone put in the effort and did their part. So you can maybe disconnect fear of having to work hard from fear of getting a bad grade. They're two separate things in this class. So you put in the work, you will get an A in this class. And I think that's one of my goals, and I succeeded last spring. I'd like to succeed again. Certainly the first bullet point is important there. I want this to be kind of a fun, collaborative, and yet challenging learning environment. Fun is a relative thing, but I'd like this to be a fun class. This is an elective class, and nobody has to take this class, right? So why have it if it's not going to be somewhat fun, kind of optional experience for you to take and learn a lot about? I want to motivate you to put in the effort to get a 4.0. I'd like to be able to do that. And certainly, my goal in any course, certainly this one, is to inspire you to learn more. If you're going to be continuing on to grad school, if you're currently in grad school, if you enjoyed this material, there's a lot of potential low-hanging fruit for like master's project, creative components, or thesis ideas that you can take from a class like this and use for that purpose. Any other questions? Otherwise, I'm going to leave things here for today. Okay, I'll be in my office. Oh, yeah, question, sure.
As we kind of take this class and we're learning about computer architecture and graphics, what other classes do you think parallel or come hand in hand to building upon this class in undergrad?
So building upon this class, not as much. This is kind of terminal for our degree program. Classes that I think are good complements to this class. That's a slightly different question. I like the CPRE, I think it's 487, 587. That's machine learning architectures taught in the fall. The other class I designed is CPRE 488 that's being taught right now. Is anybody in both classes 480 and 488 right now? Dr. Jones and I don't recommend it, but there's always a handful of students who do it anyway. You'll be getting sick of me by the end of the semester because those are my labs as well for 488. Kind of a similar design philosophy for both. Students do it, so it's doable, but you'll be busy this semester and you'll be in Coover second floor a lot this semester. But there's some synergies there as well. Some of the debugging skills that are introduced in 488 will help with this class and vice versa. So that class is a really good complement. I just think being practical, having them be different semesters is a good idea. And that's a good starting point at least. That's two other ones you can hopefully potentially take. Okay, I'll be in my office for office hours, at least for a little bit today. And I'll see you guys I'll stop by tomorrow as well in the lab, but otherwise I'll see you guys on Wednesday. Thank you.